Additional planets may exist in the Alpha Centauri system, either orbiting Alpha Centauri A or Alpha Centauri B individually, or in large orbits around Alpha Centauri AB, because both stars are fairly similar to the Sun. For example, in age and metallicity, astronomers have been especially interested in making detailed searches for planets in the Alpha Centauri system. Several established planet hunting teams have used various radial velocity or star transit methods in their searches around these two bright stars. All the observational studies have so far failed to find evidence for brown dwarfs or gas giants. In 2009, computer simulations showed that a planet might have been able to form near the inner edge of Alpha Centauri B's habitable zone, which extends from 0.5 to 0.9 astronomical units from the star. Certain special assumptions, such as considering that the Alpha Centauri pair may have initially formed with a wider separation, and later moved closer to each other, as might be possible if they formed in a dense star cluster, would permit an accretion-friendly environment farther from the star. Bodies around Alpha Centauri A would be able to orbit at slightly farther distances due to its stronger gravity. In addition, the lack of any brown dwarfs or gas giants in close orbits around Alpha Centauri make the likelihood of terrestrial planets greater than otherwise. A theoretical study indicates that a radial velocity analysis might detect a hypothetical planet of 1.8 m Earth in Alpha Centauri B's habitable zone. Radial velocity measurements of Alpha Centauri B made with the high-accuracy radial velocity planet searcher spectrograph were sufficiently sensitive to detect a 4 m Earth planet within the habitable zone of the star I.e., with an orbital period p equals 200 days. But no planets were detected. Current estimates place the probability of finding an Earth-like planet around Alpha Centauri at roughly 75%. The observational thresholds for planet detection in the habitable zones by the radial velocity method are currently 2017 estimated to be about 50 m Earth for Alpha Centauri A, 8 m Earth for Alpha Centauri B, and 0.5 m Earth for Proxima Centauri. Early computer-generated models of planetary formation predicted the existence of terrestrial planets around both Alpha Centauri A and B. But most recent numerical investigations have shown that the gravitational pull of the companion star renders the accretion of planets difficult. Despite these difficulties, given the similarities to the Sun in spectral types, star type, age and probable stability of the orbits, it has been suggested that this stellar system could hold one of the best possibilities for harboring extraterrestrial life on a potential planet. In the Solar System, it was once thought that Jupiter and Saturn were probably crucial in perturbing comets into the inner Solar System, providing the inner planets with a source of water and various other ices. However, since isotope measurements of the deuterium to hydrogen D/H ratio in comets Halley, Hyakutake, Hale-Bopp 2002T7, and Tuttle yield values approximately twice that of Earth's oceanic water. More recent models and research predict that less than 10% of Earth's water was supplied from comets. In the Alpha Centauri system, Proxima Centauri may have influenced the planetary disk as the Alpha Centauri system was forming, enriching the area around Alpha Centauri with volatile materials. This would be discounted if, for example, Alpha Centauri B happened to have gas giants orbiting Alpha Centauri A, or vice versa. or if Alpha Centauri A and B themselves were able to perturb comets into each other's inner systems, as Jupiter and Saturn presumably have done in the Solar System. Such icy bodies probably also reside in Oort clouds of other planetary systems when they are influenced gravitationally by either the gas giants or disruptions by passing nearby stars. Many of these icy bodies then travel starwards. Such ideas also apply to the close approach of Alpha Centauri or other stars to the Solar System. When, in the distant future, the Oort cloud might be disrupted enough to increase the number of active comets to be in the habitable zone. A planet around Alpha Centauri A would have an orbital radius of between about 1.2 and 2.1 astronomical units so as to have similar planetary temperatures and conditions for liquid water to exist for the slightly less luminous and cooler Alpha Centauri B. The habitable zone is between about 0.7 and 1.2 astronomical units, with the goal of finding evidence of such planets. Both Proxima Centauri and Alpha Centauri AB were among the listed, Tier 1, target stars for NASA's Space Interferometry mission, SIM. Detecting planets as small as 3 Earth masses or smaller within 2 astronomical units of a Tier 1 target would have been possible with this new instrument. The SIM mission, however, was cancelled due to financial issues in 2010.